Okay. An extension of Arrhenius is this formula that you can apply in determining one rate constant given another if we have the two temperatures here in the formula. So as I was saying a while ago, if you intend to have T1 here instead of T2 and you have T2 here in that same order as the rate constants here, you just place a negative sign before the E over R ratio. That would be good. In this case, this 2 was interchanged. Instead of writing T sub 1 here, we write T sub 2 because we wrote the ratio of E over R as positive. Now, this has an extension actually. So if you can recall in our kinetics, ln of K1 minus K2 can be changed to ln of R1 over R2. It can also be the ln of small t sub 2 over t sub 1. This t, this small t's refer to the time. Okay? These r's refer of course to the rate of reaction. Now, in the case of time class, if it's t sub 2 here, it's also t sub 2 in here. It's the only ratio here that is different than the first two, the K1 and the rate. So if it's time, if it's temperature 2 in here, it should also be T sub 2 in here. And you should have T sub 1 here. So you will use this particular ratio, ln of the ratio of the times, if you are provided with the length of time in which the reaction proceeds given the temperature of your system. You will use this data, of course, if you're given rates in relation to temperature of your system. But oftentimes what is given is rate constants and temperature, pair of data. Okay, so that's an extension of our Arrhenius equation. Now for reaction mechanism, so the balanced chemical equation provides information about the beginning and the end of the reaction. So oftentimes problems give you only one particular equation that tells you what are the reacting species and what are the final products. But however, majority of the reactions are not produced in that particular single reaction only. There are several steps that your reacting species has to be processed. That way it has to be produced, or it will produce the given product or set of products. So that's the reaction mechanism. It tells you of the path of the reaction. So mechanisms provide a very detailed picture of which bonds are broken and which bonds are formed during the course of the reaction. So simply when you speak of mechanism, it's the series of reactions that is happening in the formation of the product from the reactants. Now, the elementary step in any process is that particular any process that we can say occurs only in a single step. So, if your reaction is elementary, there is this correlation between the rate law and the stoichiometric equation. And you have only one single step for that particular reaction in the formation of the product. So that is what we call an elementary step, or a single step that is enough already to describe what happens to the reactant species in the formation of the product. Just a single reaction. Now, when we speak of molecularity, this is only applicable to elementary reactions. So we don't use the principle of molecularity to non-elementary reactions. Why did I jump to that? So the number of molecules present in an elementary step tells you of the molecularity of your reaction. So unimolecular, you only have one mole. Bi, you have two. And ter or tri, you have three molecules in your reaction. It is not common to see a thermolecular process. Statistically, they are improbable. Okay, meaning you don't have a single reaction that has three reacting species present on it. Oftentimes, what you have is just a single species or two species. If there's a need for the product to be formed from three different reacting species, oftentimes it now requires a series of reaction, not just one particular reaction for its formation. Now, the rate law for multi-step mechanism, so the rate determining step, you know this, is the slowest of the elementary steps. Now, if you recall our discussion partly on the proving of the correlation of the provided rate law, or shall I say just simply a statement that is given in the problem, and you're given a mechanism, and you are to prove that based on that particular statement, the mechanism is true for a given problem. If you can recall that in your series of steps, in your reaction mechanism, the slowest, the step that happens the slowest is the rate determining step, because the time it would take in the formation of the product is dependent on this particular slowest step, and as such is referred to as the rate determining step, or the slowest step in your reaction. Now, in your mechanisms, it's a fundamental assumption also when you're provided with the mechanism of reaction that each of the steps are assumed to be elementary. If you recall, you write the net rate equation. That way you can come up with a final equation in which you will present plausible assumptions. That way you can prove the relationship between the provided rate law and the mechanism. So that's it. So all the steps in your mechanism, reaction mechanisms, are assumed elementary. Of course, your reaction already in the first place is non-elementary, because what is given to you is the overall reaction order, or rather overall reaction already, and it does not correlate with the provided rate law. Okay, so what you just assume to be elementary are the steps in your mechanism. Okay, so this is an example taken from Brown and Lee, the book that is being used, prescribed as a textbook for Chem 110, 10 years ago, or more than 15 years ago. So unimolecular, you have this. Bimolecular, it could be this. Thermolecular, it could be this. Of course, the rate law are written here on the last column. Okay. Now, what about catalysis? So when you speak of catalysis, there's this presence of a species in your system that enhances the rate of your reaction. So it changes or it enhances or increases the rate of the reaction. So there are two types of catalysts. We have the homogeneous and the heterogeneous catalyst. So in homogeneous catalysis, the catalyst and the reaction is in one phase. So let's say when we have a liquid phase reaction, your catalyst is also liquid in state. So that's homogeneous catalysis. They are all in one phase. I think it's already a given what a heterogeneous catalysis is. So when you have a heterogeneous catalysis, of course, your catalyst here is of different phase than your system. So as such, the two will now comprise what we call a heterogeneous system. So the first step here is the adsorption, or the binding of the reactant molecules to the catalyst surface. So your species that needs to be reacted binds themselves on the surface of your catalyst, and molecules are adsorbed onto active sites on this particular catalyst surface. Adsorbed species, the atoms or ions are they are now very reactive once they get to be adsorbed on the surface of the catalyst. So this typical example of this catalyst or the solid catalyst in solid liquid systems or solid gaseous systems. You have gaseous reactants and products in the case of catalytic converters in cars. But in systems, we can have either a solid catalyst in the liquid system or a solid catalyst in the gaseous system. So the molecules that need to be reacted bind themselves first on the active sites on the surface of your catalyst. That's where they get to be adsorbed, and that's when they are rendered ready to react already. That's the very purpose of the catalyst. Now we have here irreversible parallel reactions. If you recall, we have multiple reactions then. So we have parallel, we have series, we have catalyzed and catalyzed, we have autocatalytic reactions, and we have even reversible reactions. So we're going to check on each one, go into each one, okay, briefly, before we even try to solve problems in relation to them. So you have here a parallel reaction. If you're given a parallel reaction, both reactions are considered elementary. So you are to write the net rate equation based on the two simultaneous reactions, or we also call them competing reactions. So if we express the rate in terms of the species A, then the right side of our equation will be K sub 1 C sub A plus K sub 2 C sub A. Factoring the C sub A, you will have now the sum of the two rate constants multiplied to C sub A. I know you know what to do already. You just do separation of variables and evaluate this by simple integration. Separate variables and then integrate. Now, another thing or another equation that you can set up here, this one is in terms of the species A. And since it's present in the two reactions, you need to account for the two reactions in the net rate equation. So this is it. When you want to account for product R only, since it's on the first reaction only, then you write it as dCr/dt, positive already because it's a product, and it's still expressed in terms of K sub 1 C sub A here. I like to make this specific. This K sub 1 class is K sub R, the specific rate constant in terms of product R. Because if it's K sub 1 here and it's K sub 1 here, you will get mixed up because the rate constants are really different if we're basing the rate of reaction on a different species. Different species, different rate constant. Let me just change my font so you'll be able to see properly. Make it to red. So this K sub 1 is actually K sub R, C sub A. Okay? The rate of formation of product R is equal to K sub R C sub A. The rate of formation of product S in your second reaction is K sub S C sub A. That way now we represent specifically the rate constant in terms of the species in which we base our reaction rate. In this case here, this K sub 1 and K sub 2 are the rate constants based on A, because we're writing the net rate equation based on this reacting species A, okay, that is present in this competing reaction. Okay, take note of these formulas here. Okay, we'll go back to them in the problems that we will cover next meeting. Okay, then we have this. So for parallel reaction, C sub A plus C sub R plus C sub S is a constant. At any particular time, the remaining amount of A, the amount of R formed, and the amount of S formed will be a constant. The sum of these three will be a constant at any particular time. As long as, of course, your stoichiometry is like this. We change the stoichiometry. What do you mean by that, Miss Ali? You change, let's say, for example, if you write 2 here, or if you write 2 in here, this one will not hold true anymore. The one that was shown to you a while ago. This particular, where was that? This one. So will not hold true anymore. You go back to material balance wherein you use the stoichiometric relationship of the species as they are written in your reaction. But most of the parallel reactions that I have encountered, class, will always have 1 mole of A here where the products are being formed. So it could be somehow altered by changing the coefficient of any of these two products. So in the sample problem that we will be tackling next meeting, it will not be in this same form. That way you will get used to not having the original form of the reactions as given in our textbook. That way you will know how to handle situations wherein it's not anymore similar to what level spill is giving. So in this case, if you have if you have this competing reaction, then this holds true. The first equation yields a plot with slope equal to k sub 1 plus k sub 2. This one is taken from the net rate equation based on species A. And this is our formula. While this was taken from these two. Where was that? These two. You take the ratio of these two, or you divide one by the other. So RR over RS, you will have dCr dt over this CS dt. The dt's get to cancel each other. That's the reason why you have this one. And this K1 and K2 actually is this 2. K1 divided by K2. The C sub A also cancels each other. So specifically, I'll write now in here that if we have rates in terms of product R and S, it would be K sub 1, or rather K sub 1 now written as K sub R, and K sub 2 written as K sub S. Okay? Now, what about this one? Where did this came from? This one. Okay? If you will do separation of variables here, anyway, these two are just constants. So if you're integrating from initial concentration to final concentration, so you will come up with this. You just transfer it there and then place it back again in here. So your dCr is actually this delta C sub R, the change in the concentration of R. Your dCs is the delta of C sub S. You have this, and specifically this is again K sub R and K sub S. Now, these equations will come in handy when you are given a competing reaction to process. So, depending on what the problem requires you to solve. Now, this will change. This relationship will change again if the stoichiometric equation is changed. We change this one. We change any of the coefficients here. This also changes. So this is just only 1:1 because as you could see here, you have 1 mole of R, 1 mole of S. Okay? In this is the actual reaction that is given in Levenspiel, just to present to you the principle of deriving the appropriate formula for an elementary parallel or competing reaction. Okay, let's proceed. So for a homogeneous catalyzed reaction, you have the presence of the catalyst. Of course, because it's catalyzed. When you write the net rate equation, class, just like in competing reactions, you account for, or you write the uncatalyzed and the catalyzed reaction. So this is your original homogeneous reaction, for example, of A being converted to R. When it is catalyzed already, you account for the presence of the catalyst. So it has to be written in the left side and in the right side of the equation, even though it doesn't participate or it's not being consumed. Its sole purpose is to increase the reaction rate. So now you are to write the equation for the first, the uncatalyzed and the uncatalyzed reaction. So this is for the uncatalyzed. This is for the catalyzed reaction. You could see here that you already have the C sub C. The concentration of the catalyst, which is of course kept constant. It will not change in the course of the reaction. You will have to write the net rate equation as I have said. Just go down. And this is how you're going to write it. So you have to get the sum of the two reactions. So you have now this one, and if you factor out, so if you factor out the concentration of A, since it's common in the two terms here, you will have the quantity K sub 1 plus K sub 2 C sub C. Okay, and this is your C sub A in here. Then do separate variables. You separate variables and integrate, this will be your equation. We call this as the observed rate constant. We call K sub 1 as the rate constant of the uncatalyzed reaction. We call K sub 2 as the rate constant of the catalyzed reaction. Okay, K sub 1 and K sub 2. The way you process the DCA over CA in here is the same with first order reactions. So the left side here is comparable to that of the first order reaction. So we only have this right side as the thing that makes it different than first order reaction. So for your homogeneous catalyzed reactions, you are given instances wherein the concentration of the catalyst is being varied. And based on the different concentration of the catalyst, how well is the reactant, let's say A, is being converted to the product, or how fast is it being converted to the product? How fast is it being converted, or how fast is it being consumed? Okay, so this is the main equation that you should not forget regarding homogeneous catalyzed reactions. So making a series of runs at different catalyst concentration will allow you to solve for K sub 1 and K sub 2. Now, if you again go back to the plotting, if you plot the line, so the slope of that particular line is the K observed. And if you plot the different K observed values for different catalyst concentration, you'll be able to determine the rate constants of the uncatalyzed and the catalyzed reaction. But you won't do plotting. You will analytically solve for what the problem requires. This is just for your information. Okay? And you will be given a problem also as an application for that. Now, the homogeneous catalyzed reaction will happen even if there's no presence of the catalyst. So it will occur without the presence of a catalyst. Just a few minutes, class, huh? Now, for the autocatalytic reaction class, initially it's a requirement that there has to be an amount of R that should be present. Okay? Homogeneous catalyzed reaction does not require that there should be an initial amount of catalyst present. This one requires it that there should be a little amount of the product present initially. So in here, one of the products of reaction acts as a catalyst. So your product R here acting as a catalyst. So it's present now, written in both the left side and the right side of the equation. And if you're going to write the rate equation, it would be like this. Now you take into account the concentration of the R, which is the product, which has a catalytic effect on the reaction. So the number of moles of A and R in this particular type of reaction remains unchanged as A is consumed. Now, the relationship that we are to take note of, as long as this is our stoichiometry, is the one that you see below. The initial concentration, or the sum of the initial concentrations of A and R, will be equal to, or should be equal to, the sum of the concentration of A and R at any particular time for a autocatalytic reaction. So it's a constant. In here, there's no need for you to write any net rate equation because you only have one equation. You only have one stoichiometric equation. So from in here, you can see that the sum of the initial concentrations will be equal to the sum of the final concentrations. Let's say we will represent it as C sub O. There's a need for us to express the C sub R here in terms of C sub A. It's because our unknown function here is C sub A. So we cannot evaluate our DE if we have another variable here. We're limited only to two variables. In this case, it should only be C sub A and time. In that case, the C sub R is expressed in terms of the C sub O here. And C sub R then would be C sub O minus C sub A. And that's what's being done in here on the next slide. So the C sub R is replaced by C sub O minus C sub A, which upon rearranging and breaking into partial fractions and integration, so this could be this C sub A and this C sub O minus C sub A can be placed in here, the dt could be placed in here. You can process the integration part using method of partial fractions. The formula for this autocatalytic reaction would be something like this. Excuse me. Where your M, if you set M equal to the ratio of the initial concentration of your product R and your CaO, then this particular equation becomes this one. Okay? For an autocatalytic reaction. Actually, there's no need for you to memorize this because I'm sure you have an equivalent formula available in your handbook. If it's not there, you can easily have it derived because I know you know how to separate variables and do your method of partial fractions. The only thing is if you are in a hurry and you are in need of more time to do the processing. So that's where the importance is of the, shall I say, the photographic memory. There are students who are really good in memorizing. So if you are that, capitalize on that, memorize formulas. If your memory can still help you with that. That way, you need not go back to derivation. So it helps to memorize, especially if it's not in the handbook, and it also helps to memorize if you know well your handbook, in which particular location in your handbook can a particular information be found. The very importance of why you need to be well versed of your handbook, not that you only get to see your handbook during reviews. It's very important that even starting last year you already know which particular part of the handbook will you have to open to if you need a particular information. Okay. Now, so based on what I have said a while ago, so some product R must be initially present if reaction is to proceed at all. So I've mentioned that already. The rate will increase as more R is formed. It's a given. So as more R is being formed, since it has a catalytic effect, then the rate will increase. When A is about to be used up or consumed totally, your rate will drop to 0. Now, when will be rate maximum? Rate is maximum when the concentration of A and R are equal. This is when rate is maximum. Now, the plot of the time in the concentration for autocatalytic reaction yields a straight line passing through the origin. So, meaning it does not have any y-intercept. Okay? That's in the case of your autocatalytic reaction. As this one is very important. It's needed that you should have R initially, and rate is maximum when A and R are equal. Very important information regarding autocatalytic reactions. Now we proceed. Now this one is for a series reaction, a two-step series reaction with intermediate R and final product S. You know this one? I'm sure you know why is it like that. A is being consumed in the first step, so this is the rate equation in terms of A, and this is the final working equation. After doing separation of variables, this is your formula to use in determining the remaining amount of A given the time. The problem will give you oftentimes the initial concentrations and the rate constant. Okay, what about the intermediate? So when you write the intermediate R, it's in the form of a rate equation. Why am I saying it's in the form of a rate equation? Because your R is present here in the first step and in here on the second step. So you will have two terms in your net rate equation. If R is to be written in the form of a substance that is being produced, then it should be written as positive, and K sub 1 C sub A should be positive as well. So based on the first reaction, it should be K sub 1 C sub A. Based on the second reaction, it should be K sub 2 C sub R. But this time, it should be negative because this time R is your reactant, not a product anymore. So you have here negative K sub 2 C sub R. Now, the problem with this problem or this equation is that you have a K sub 1 C sub A here and a K sub 2 C sub R here. But you have your linear DE for that to thank for. So you transfer this K sub 2 C sub R in here. And this is already comparable to a linear DE. This is your derivative. This is your P of X. And this is your X then, if our variable is X and Y. P of XY. And notice that your CA here, since you cannot have a CA here, since your unknown function is C sub R. So you cannot place CA here. So you change the CA in terms of this formula in here that you got from the first step of your two-step reaction. So express it in terms of CaO because its only variable there is time. CaO and K sub 1 are constant. So you do that in here. And this is already a linear DE. The process of finding the solution of that linear DE is dependent how well is your memory or your recall of linear DE. You find the integrating factor and then you multiply that integrating factor with your unknown function here, C sub R, equate it to the integral of your integrating factor and the entire expression that you have here, your Q of X. We call it then Q of X in DE. This is P of X, Y. Q of X, this is dy dx. That's how we do it. But then, this is your formula now, using your DE. What is the purpose of this formula? It will allow you to determine the amount of R present at any particular time. And there are really problems that came out in the board exam about this. Okay? Determining the amount of the intermediate at one particular time in the course of the reaction. So in here, you only be needing the rate constants, K sub 1 and K sub 2, and the initial concentration. So since they are constants, if you know the time, you can determine the amount of the intermediate at that particular time. Okay? Now we proceed. What about the final product S? So this is what we're interested in. The final product S in our two-step reaction. If you're going to write its rate equation, it would be K sub 2 C sub R. Here, K sub 2 C sub R will be forming S. Okay, we have it here. This will be processed using two procedures, but what I wrote here is the easiest of the two. You can change the C sub R here. You see this C sub R. You can change it in terms of this one. This entire expression, you write here. Why? Because you could see in here that you only have time. All are constant. So if you're going to write it in here, it's so easy for you to process. You just transfer the dt in here and have all of those terms there integrated. Anyway, they are just exponential in nature. So integral of an exponential function is easy. These are constants. So you just place in here. But the easiest class is this one. Noting that there is no change in the total number of moles for your two-step irreversible reaction in series, then what you have here is that the initial concentration of A is equal to the sum of the final concentration of A, that part that is left, the amount of R and the amount of S. Let's say, for example, in this reaction class, on starting only with A, so there's no R and S initially present. What about if you already have R and S initially present? All you have to do is add it here. So CaO plus CRO plus CSO is equal to Ca plus Cr plus Cs. Anyhow, the amount of R and S that is formed will be coming from in this particular formula, will be coming from the A that is being consumed. So, at any particular time, the total number of moles in your two-step reaction should be equal. Wala may nagdugang, kaya ang naiban sa isa na form man into something. So that's it. So you just add here the initial concentrations of the intermediate and the final product if they have initial concentrations available. Okay? Now, if you do that, class, this is your formula for the C sub S. We just take the formula for Ca in terms of CaO. We take the formula for Cr in terms of CaO, K1, and K2 also. And you'll be getting the C sub S. Okay, so this is your formula for that. Now, transfer mo lang ni siyang Ca dira ho kagang Cr. You will be getting the C sub S here. Okay, now, what about the next here? These are generalization based on the formula that was shown to you here on the formula in determining the final concentration of the end product. This is where we're really interested in. So if we're going to look into the formula for determining the final concentration of the end product, just simply look at this particular generalizations here made by Levenspiel. If the second reaction is much larger than K sub 1, then the rate of reaction or the amount of the product is solely based or dependent on the first step. Again, going back to that very fundamental concept in Chem 1, that the rate determining step is the slowest step. And since K2 is much larger in this scenario than K1, then the amount of the final product formed will be only dependent on the first step. So CaO 1 minus e raised to negative K sub 1 T. Now, this formula can also be derived from here using that premise that K sub 2 is a lot larger than K sub 1. So in that case, if K sub 2 is a lot larger than K sub 1, your entire second term here will be very small compared to this one because K sub 2 is very large compared to K sub 1. That's the very reason why you have this formula written here. It's only dependent on the first step. Going back mathematically to the formula, because you use that same principle when you determine the order of the reaction. If one step is dominating over another, we will reach that particular portion. So if K sub 2 is a lot greater than K sub 1, this will be gone. It will be more of K sub 2, and since you have K sub 2 here, it will cancel with this, leaving you with this one here. So that's the reason why you have formula that is dependent only on the first step. Get it? Mathematically, it's like this one has no effect to this. We know that this one is already more or less 0. And this one is very small compared to this. It's just like it's gone. You have this, so cancel also, so negative. Okay? Either which you look at it, you go back to Chem 1 or you go back to the equation that you derived, you will still arrive at the same simple formula if K sub 2 is much larger than K sub 1. If K sub 1 is much larger than K sub 2, of course, it would be the K sub 2, which would be the rate determining step. So it will be the one that will be appearing in the formula in determining your final product C sub S. So reaction will be governed by the slower step of the two-step reaction. Or that's your rate determining step. Now, what do I have here next? We have a ready-made formula class, but this formula will only work, I'd like to emphasize, if K sub 1 is not equal to K sub 2. And if we are provided with the same stoichiometry, and that's A forming R forming S. If any of the species here have a different coefficient, this particular formula will not work anymore. The same thing with this. So solely for this particular condition. If your K sub 1 is equal to K sub 2, if you recall, you were given a problem set wherein you are to derive the time when your R your intermediate R is maximum if K sub 1 is equal to K sub 2. Then use that particular formula. From that particular formula, you will get the maximum concentration of the intermediate R. So determining the time when intermediate is maximum and what is its value is dependent on in this limiting information. So the formulas you see here will work as long as stoichiometry is like this and the rate constants are not equal. If not, as I've said, you have already the pre-derived formula then assigned to you in the form of a problem set. So this will be the formulas. If you look closely, the formulas are simply functions of the rate constants. Now, what are our generalization regarding this irreversible reaction in series? So your initial species, reactant species A, decreases exponentially. Why do we say it's decreasing exponentially? Because of this. It's decreasing exponentially. It's supposed to be decreasing because it's being consumed. So that's one generalization there. R is expected to rise to a maximum value and then falls and S rises continuously. So there will come a time that R will be maximum. We determine even the time when would that occur. And S is expected to rise continuously because it's our final product. The greatest increase in S, take note of this. When is the greatest increase in S observed? When R is maximum. That's the very reason why you have a pre-derived formula of when will R be maximum and what is its value. Because that's when the greatest rate of increase in the final product S is observed. Now, K1 and K2 can be evaluated by noting the maximum concentration of the intermediate and the time when this concentration is reached. It's referring to these two equations which you will need to solve simultaneously. So knowing the time when R will be maximum, you have an equation in terms of K1 and K2, and knowing an equation that will help you solve for the maximum concentration of R. If it's known, you have two equations, two unknowns, you will solve for the two rate constants. So that's how important are these two equations in determining the rate constants if they're not given. So it would really help class if you have memorized the formula for a scenario where in K sub 1 is equal to K sub 2 for these two needed information. This is being asked if you're given a two-step irreversible reaction in series. Okay, that way you can determine the K1 and K2. Okay, now I think we're almost okay. Sige lang, kundi ilan ta matapos. Now we go to reversible reactions. Chem 1 teaches you that many reactions are reversible due to the fact that no reaction ever goes to completion. So there is no such thing as XA equal to 100%. That's just a hypothetical question. But there is no particular reaction that accomplishes 100% completion, meaning all reactants were consumed and the expected amount of the product produced. It's because that there is some degree of reversibility in all reactions. The reason why it's written as irreversible is because the rate of one really dominates another. So it's like the rate of the reverse reaction is very small compared to the forward reaction. So that is why you only get to see one path. That is it's written as an irreversible reaction. Now, irreversibility increases as the equilibrium constant K sub C increases. Now, speaking of the equilibrium constant K sub C, some books would write it as this. It's equal to the ratio of the rate constants of the forward and the reverse reactions. And it's also equal to the concentration of the product. So I will write here product raised to the exponent, its exponent in the balance chemical reaction and reactants. So if you have several, you just write let's say this is N. You just write the products of these concentrations here. Several products raised to their coefficient in the balanced chemical reaction. Several reactants raised to their coefficient. So you just take the product of those, and you will have the denominator and the numerator for this equilibrium constant expression. One thing very important, and I don't want to miss mentioning this ratio of the concentrations of the products of reactants, of the concentrations rather of the products and the reactants will be measured or should be measured at equilibrium. It should not be any particular concentration measured at any time. This concentration should be measured at equilibrium. Okay, so the irreversibility of our reversible reaction increases as the equilibrium constant increases. Now, this is for your first order reversible reaction. I'm sure you can still recall that when you write the net rate equation, either in terms of the product or of the reactant for a reversible reaction, it's in the form of a net rate equation. As you can see here, the rate of reaction in terms of reactant A is equal to K sub 1 C sub A. It's being consumed in the forward reaction and it's being produced in the reverse reaction. So minus K sub 2 C sub R. So you write the net rate equation for the species, whether it's the reactant or the product for a reversible reaction. Just like the way you do it with homogeneous catalyzed reaction, just like with parallel reactions. So the same principle holds true with this one. Okay? If this is dCA, this should be expressed in terms of CA. If this is XA, this should be expressed in terms of XA in the same way that this should be expressed in terms of XA. How? You go back again to the stoichiometric equation and use the stoichiometric equation that I have given to you a few minutes ago. Okay? The amounts reacted and the amounts produced based on the location of the species in the chemical reaction. So if you're going to simplify the right side in here, it would be something like this. Okay, making your DE homogeneous in terms of the unknown function. So what is being written here is a DE in terms of the unknown function XA. You can have your own DE in terms of the concentration CA, but this would be your left side. And you just change the C sub R here in terms of CA. Now, it's already written here. K1 and K2 are the rate constants of the forward and reverse reaction. That's reverse reaction respectively. Okay, let me see. You have here a formula in determining the equilibrium constant. So it's very specific the way it's written in our book, that the conversion is conversion at equilibrium because the concentration should be concentration at equilibrium. And you have here the ratio of the two rate constants. You have this. The final formula is this one, class, for a first order reversible reaction. Now, all first order irreversible reactions, sorry class, this is reversible. All first order reversible reactions are simply special cases. Okay, I stand corrected. This is right. I've written it as irreversible. Are simply special cases of reversible reactions in which the concentration of A at equilibrium is already 0, or the conversion at equilibrium is 1, and as such, the equilibrium constant is infinity. Primarily because you have conversion already equal to 1, and this one specifically it's already equal to 0. So you will have here division by 0. So your equilibrium constant is infinity. So you have here conversion concentrations at equilibrium, conversions at equilibrium, and rate constants. So your equilibrium constant can be solved in any using any of this equation, whichever is easier to use. Okay, last on reversible reactions, the second order reversible reaction. So it could be in this form, it could be in this form. So this have the same left side, the product side, the two different representations here, and this also. So one species, two moles for each species, and you have this as the product side. So in here, the formula that you are seeing, I'd like to emphasize as pre-derived already, is applicable only if CaO is equal to CbO and there are no amounts of RNS initially present. So meaning there are no products initially present. And in the case of the left side here, your CaO and CbO, initial concentrations of the two are equal. If you're going to process the net rate equation, you're also going to write the net rate equation just like this one here for a first order reaction, following the principles of how to write the rate law, considering the forward and the reverse reactions as elementary reactions. This will be your formula. But it's only applicable, as I've said, in this scenario. When your CaO and CbO are not equal anymore, this will not be of use. You are to write your own net rate equation based on the problem or based on the information that is provided in the problem. Okay? Now, for tonight, we have covered the integral analysis for constant volume reactions. So next meeting, we will have the variable volume reactions, and then we'll proceed to sample problems on kinetics before we go to reactor design. That way, you can right away apply what we have discussed. So before I go to variable volume, next meeting, I'll first discuss problems or give you concept questions regarding what we have discussed tonight. Okay? Any questions, class? No questions? Stop sharing.